Good morning, AP Chemistry. Chapter 7, we're going to go through the atomic spectrum of hydrogen and discuss the Bohr model of the hydrogen spectrum. So Bohr revolves all around hydrogen. And we're off. Okay, so the atomic spectrum of hydrogen. This section is section 3 in your book. White light exhibits a continuous light spectrum, meaning it contains all the wavelengths of visible light in a continuous stream of color. And again, there's your Roy G. Biv in a one long stream, no breaks of color. That's continuous light. Niels Bohr discovers that hydrogen gas shows only a few visible lines of color on its spectrum. It displays only certain visible light wavelengths, not a continuous stream of color. If you notice, that emission spectrum of hydrogen shows 4 colors. This one is at 656 nanometers. This one is at 486 nanometers. You have a 434 and a 410. And if you were to use Planck's calculation to determine energy of each one of these wavelengths, your energy and it would also be times 10 to the 19th. I just can't fit it in. And notice as we go from the shorter wavelengths at this end here to the longer wavelengths over at this end, your energy is decreasing, which of course is the relationship between wavelength and energy. Bohr model, notice hydrogen only. Keep in mind, the minute he started going on other substances, his theory started breaking apart. Niels Bohr, German guy, only works with hydrogen. The effective nuclear charge Z is +1 for hydrogen. White light emits a continuous spectrum. We just discussed that. Hydrogen has a line spectrum. I just showed you that. Hydrogen's line spectrum proves discrete quantities at particular wavelengths, quantum of energy, not continuous. Hydrogen also contains wavelengths that are not in the visible light range, so it's not limited to just visible light, but it's still got discrete quantities at different wavelengths, infrared, ultraviolet, so it's got other wavelengths, not just limited to visible. Only certain energies are allowed, meaning it's quantized, not continuous. Change between levels will produce a certain wavelength of light being emitted or absorbed. So the Bohr model of the hydrogen and only the hydrogen atom. And what I want you to do is realize a couple of things. I want this recreated in your notes exactly as you see it. Notice that the energy levels, as you go away from mama nucleus, and I call it mama nucleus is dead center here. As you get away from the nucleus, the energy levels get closer and closer and closer. So you can imagine what the distance between n equal to 18 and n equal to 19 and n equal to 20 must be. They must be almost on top of each other. So when you draw this, make some notations. Make sure you draw it exactly as you see it. There's a large gap between energy level number 1 and energy level number 2. Pretty big gap between 2 and 3, but the gaps start getting smaller the further away from the nucleus you get. Bohr also thought that the electron orbited the nucleus in perfect concentric rings. That's why this model is drawn this way. things to write down that you've seen before in first year chemistry. He called them orbits and calculated the radius of the orbit as n squared. And n, of course, is staring you in the face, 1, 2, 3, 4, 5, 6, 7, 8, to infinity. N can go to infinity, remember that. N is the principal energy level. N is equal to 1 is the lowest energy level. It is the closest to the nucleus. It is the most stable. It's where the electrons belong. As N increases, as you get further from the nucleus, the energy increases and the electron is further from the nucleus. So the further away from the nucleus the electron is, the higher energy that electron has, which is unstable. The electron wants to be in that very first energy level and wants to have really low energy. Infinite number, so n can be, goes to infinity. All right, more pieces of information about the Bohr model of the atom, the hydrogen atom. You already know this, we discussed it. Energy is quantized. It is not continuous. It spits out certain wavelengths of light or absorbs certain wavelengths of light. The Bohr equation is used to calculate the energy of the electrons. Actually, the Bohr equation is used to calculate the energy of the orbit, and if the electron is sitting in that orbit, then the electron has that energy also. And again, units, please keep in mind that it's just a matter of units. This is the one you will be most familiar with. This is the one we'll use most often because it's going to give us some aesthetically pleasing numbers. That times 10 to the negative 18, especially when you're trying to compare whether it's larger than or smaller than, gets a little dodgy. So this one that I circled is the one we will be most familiar with, the one we are using all the time. So a couple of things to go over with this guy. This 2.178 times 10 to the negative 18 joules is the Rydberg constant. We can convert this. .178 times 10 to the negative 18 joules is per one single photon of light. So we can convert it to kilojoules per mole with this little quick computation. And what do you get? You get the Rydberg constant in kilojoules per mole. So it's not that they're different numbers, it's that they're different units of the same number, and this is the one we will use most often. All right, so we're going to do a little computations here. I am going to calculate the energy of the first, I guess 6 levels in the Bohr model. And again, here's your Rydberg constant for the Bohr model, and the orbit's radius. All right, so I just calculated the energy of the first 8 orbits in the rings of the Bohr model, and the electron is experiencing this energy as it sits in this orbit. A couple of things to notice. First off, further away from n is equal to 1, which of course is the principal energy level, the further away you go, notice that the energy is increasing. It's getting closer to 0. Also notice that they are all negative signs, and we're going to discuss this in a minute. Why are they negative? How can you have, this is like the very first time and the only time that these negative values actually tell you less than 0, because of course this is a hypothetical theory by Bohr, and he assigned an electron completely removed from the orbit as having an energy of 0, and anything in the atom as having an energy less than 0. Well, how do you depict energy less than 0? You give it a negative sign. These energies here that I calculated are not telling you direction. They are telling you that the Bohr model assigned negative energies, less than 0 energies, to the electrons sitting close to the atom. And of course the one that's closest has the smallest energy, because it of course is the largest negative value. It is way less than 0. And as you move away from the nucleus, the Bohr model of the hydrogen atom depicts the energy increasing until the electron is completely removed and it's a 0, and then even greater than 0 as it gets further from the nucleus, completely removed from the atom. So that's a couple of things you've got to wrap your head around, because all the other times that negative sign's always been direction. In this situation, it is not direction. It is actually the value of. So I'm going to pick some random, I'll say, what about the energy for energy level 2862? What's its energy? Well, you're going to do the exact same computation. Your energy for this level, according to Bohr, and as you get further from the nucleus, you are getting closer to 0. You are increasing. You are increasing the electron's energy as you get further from the nucleus, and that's a bad thing because it's an unstable thing. Electrons can move from one energy level to another, up or down. When an electron jumps down, it must lose some energy. How? That energy is given off as a photon of light. It's the difference between a higher energy level and a lower energy level. The electron does not need it. So if the electron is in the 6th energy level sitting here, it has an energy of 36. If it moves down to number 2 here, in order to sit in number 2, it needs a lot less energy, because again, the negative sign means less than 0. And the difference between these two numbers means it emitted, the difference between these two numbers, the negative 36 and the negative 328, means it emitted 292 kilojoules per mole of energy. Doesn't need all that energy when it sits in a lower level. So where does all that excess energy go? Out. Out as what? Out as light. And you're actually going to be able to calculate the wavelength of this 292 kilojoules per mole. If an electron wants to jump up energy levels, it must absorb enough energy to get to that level. So if we were going in reverse order, let's say the electron in number 2 wanted to jump up to energy level number 6. Means you're going to have to absorb 292 kilojoules per mole for the electron to jump from the 2nd energy, which is lower, to a higher energy in order to get to that higher level. All right? And this light, this energy that is either being absorbed to move up a level or emitted when it moves down a level, is a photon of light. And in our case, we're going to calculate a mole of photon of light. Okay, so the change in The change in energy of an electron during a transition, either moving up or down, will be delta E being equal to E final minus E initial. So that's your final level minus the energy of the initial level. You will get a negative sign if it's being emitted. So when you get a negative sign when you do this computation, negative means that the photon of light is being emitted. If it comes out to be a positive value when you do this computation here, that means that it is being absorbed, which makes sense. You are going to move up energy levels. You're going to a higher. You are going to need an external source. You are going to need to absorb energy to move up that level. You can't just do it spontaneously. It's not going to happen. Coming down, you're going to emit all that excess, and it's going to be emitted as a photon of light at a particular wavelength, at a particular energy. The other little piece of information which you should remember from last year is there's no such thing as a negative photon of light, a negative energy for a photon of light, so it's just the absolute value of the change in energy. In this situation, that negative sign tells you direction. The negative sign just tells you it's being emitted. So when they ask you for the photon of light in kilojoules per mole, you're going to drop the negative sign and say, well, the photon of light is 292 kilojoules per mole. You'll notice in my example, I didn't leave the negative sign on there. Emission means dropping down a level, a negative value. All right, so I am going to do an example. Calculate the energy in kilojoules per mole, because that is our most popular unit, and wavelength of light emitted during a 5-to-1 electron transition. Would we be able to see this light? So a couple of things I'm going to write down. I am dropping down from energy level number 5 to energy level number 1. So I should expect to get a negative delta E. All right. So the energy of the photon would be the positive of this value, and then we use that for wavelength. Second question it's asking is, once you've calculated this, and you've calculated the wavelength from this, does this fall in the visible light wavelength range, 400 to 700 nanometers? And that's what we're going to figure out. Transition, whether it's moving up or down, is going to be the energy of the final orbit minus the energy of the initial orbit. If the electron's sitting in the orbit, that's the energy the electron is being exposed to. The equation to calculate the change in energy of the transition, instead of calculating each individual energy, which you can, the lump sum of it all is negative 1312 kilojoules per mole, which is the Rydberg constant in kilojoules per mole, times Z, which is effective nuclear charge, which of course for hydrogen is 1, so that's easy, over the radius of the final orbit squared, minus the effective nuclear charge for hydrogen, which is 1, so that's easy, divided by the radius of the initial orbit squared. So this is nice and simple. Just plug everything in the right place, and it becomes this guy here. the change in energy that is either emitted or absorbed, but in this case emitted because it's dropping down from 5 to 1. And sometimes you'll find me putting a little notation here, is a negative 1312 kilojoules per mole times 1 divided by 1 squared, which is the final orbit, minus 1 over 5 squared, which is my initial orbit. Plug it into your calculator. This negative sign is purely directional. I said earlier it should be negative, and it is, because it's dropping down. Drop the negative sign. Here's the energy of the photon of light that is being emitted when this electron drops from 5 to 1. And again, we like the kilojoules per mole because it just gives us a better number than that times 10 to the negative 19 business. All right, so there's our first step. Here's the amount of energy released, emitted, when that electron drops from 5 to 1. And if you were to go back and do the difference between the fifth energy level and the first energy level, fifth being 52, the first being 1312, you'll find the same thing. So 1312, the difference between 1312 and 52 is the 1260. So it correlates. All right, second step. What wavelength is that? I can't determine if it's in visible, infrared, ultraviolet based on energy. I need the wavelengths because the electromagnetic spectrum is listed in wavelengths. So I need to do the computation to change this from energy to wavelength. Here it is, using basically Planck's constant and stuff like that. And again, the units are different. I used Planck's constant in kilojoules seconds per mole instead of joules seconds, and I used my speed of light in nanometers per second. And you should be familiar with this from first year chemistry, especially the 119-700 you came across there. It's just a shortcut. Write it all out this way or just use the shortcut. Either way you're going to get the same answer. The wavelength for that photon of light, I beg your pardon, for the mole of photon of light being emitted for a 5 to 1 transition is 94.9 nanometers, way smaller than the 400 to 700, definitely not visible light. And that's what we're going to do repeatedly. So a couple of pieces of information about the Bohr model, especially the fact that the energy levels are literally a negative value. The only time that negative sign does not tell you direction actually tells you that it's less than zero energy, which of course is not right, which of course turns out to be disputed when we get into quantum numbers. All right, so why are they? Bohr hypothesized that an electron completely removed from the nucleus of an atom will have a zero energy state, or even higher if it's further away. Now again, high energy is a bad thing, especially in chemistry. You want everything to be a very low energy. A high energy is unstable. So once he established that the electron removed is a really high energy, like 0 or greater, he had to depict the energies bound in the nucleus as lower than 0. Well, the only way to make something lower than 0 is to make them negative values. So he literally assigned less than 0 values to the energy orbits of the nucleus.